So if you see it practically, if you make a hole at point here and a hole at point here, you'll see the pressure, the water shoots out faster than here. Why is that? Because the pressure is high. How can you see it? So think about the pressure at point 1. It's the atmospheric pressure plus the pressure due to the weight of the water column out here. So which is the density of water into the acceleration of gravity into its edge. You see the weight of water. This is the weight of water. And P2, P atmospheric plus rho g H2. Now see, since H2 is greater than H1, P2 is greater than P1. So this is the pressure energy. The energy that we get due to the pressure of the liquid above. Okay. Now coming back to the previous question, what I was trying to solve right now. I forgot where I was. Okay. Coming back to the same equation. This thing. P atmosphere, P1 is P atmosphere plus the weight of the water column above it. So this H, I'm just putting the heads. So in the case of atmospheric pressure, the head is, it's not exactly P atmosphere, I did this mistake, it's P atmosphere, always correct me, divided by rho into G. To get the head, you always divide it by divide the energy with the density of the liquid and into the acceleration due to gravity. These are terms basically head. It's easier to make calculation by using a head than rather than using the energy term. So okay, plus Z1 plus V1 square by 2G. Oh yeah, yeah. Equal to P2 is P atmosphere by rho G plus my handwriting is legible, right, for you? Because this marker is too fat and like I get this and the board is too small. So P atmosphere plus H minus Z2 plus Z2 plus V2 square by 2G. Okay. And okay. So we will cancel H minus Z1. Z1 will cancel. And H and H cancel. Z2 Z2 cancel. So V1 square by 2G is equal to V2 square by 2G. And V1 equal to V2. So the velocity of water in here and here is the same. And it makes sense because they are in the same column. It's a solid mathematically. Okay, so basically velocity, and it will be used later. And in this problem, in our equation, we'll take it to be negligible compared to B. To make our calculation simple. Okay, did everyone get this? Okay, thank you. Thank you. Okay, so now let's go to the problem in hand. RFS. Okay. So now what we do is for the orifice, probably we take a point here and a point just outside of this thing. Okay. So take a Bernoulli equation. If you do it, let me write it here. And one thing you have to know is, wait, I'll come to that later. Let me just, so one thing at a time. Yeah, don't jump, Annesh. Okay. So how do you solve this? Now, P atmosphere by rho g plus point here is this h plus, and take the datum out here. Okay, plus h minus h. This is the pressure term. Plus elevation term. The potential energy is 0 because the datum is out here and the point is at the datum. So this is 0, and we assume that the velocity is negligible in here compared to here. So this is also 0 at 0.1. So this is what 0.1 is equal to this at 0.2. So at 0.2, there is no head out. At this point, just outside of this thing, there is no liquid above it. So it just P atmosphere by rho g plus, again, the elevation, they're both at the same point. So this is 0 plus the kinetic energy. Now these both get cancelled. So v square by 2g is equal to h minus h. So v equal to under root 2g h minus h. So to put it simply, if you take a liquid where the orifice is at a height small h from the water surface, the velocity is equal to under root 2gh. Basically, it's the height difference between the orifice and the top of the water surface. This is only if the orifice is free flowing, like the water is being, the water level is always, it's always flowing outside the water, like it's going to air. If by any chance it's like this, basically the water is not flowing to the air, but it's flowing to another tank. Okay, and this is h, this is h1, this is h2. Now let's try solving. The atmosphere by rho g, at, you can take 2 points here, 0.1, 0.2. The atmosphere rho g plus elevation, wait, plus h minus h1 plus velocity 0 is equal to, okay, now tell me what will be the pressure head out here. See, it's not open in the atmosphere, there's a liquid column out here. So the atmosphere by rho g plus h2 minus h1 plus v square by 2g. So cut V is equal to under root 2G H minus H2. So it's basically the height difference between the two water columns. Okay, everyone got it? So, any questions? Because now I'll go on to orifice flow. Like,
Sorry,
yes.
I have a question.
Yeah. You can ask by the chat or something.
Sorry. So my question is, why there's like a velocity on the right side? Because I seem to like I can't imagine that velocity. So it's like the water table is going down or going up. Is that velocity?
This velocity, why I took it to be 0? The velocity out here, right?
No, I mean the velocity on the right hand.
Yeah. Okay, here. Yeah, so that velocity you are calculating. V equal to, what's the question? Like, that's the velocity you are calculating right now. That is the velocity at which the water flows from here to here.
But I mean that you are calculating the energy conservation on the left water table and the right water table, right?
Yeah. The energy conservation between at point here and point here into this, not at water tables, at these points.
So why at these 2 points, like there's no velocity at the left point, but velocity at the right point? I mean, water is going from left to right, so it should have velocity on the both sides.
Because at this point we take it to be like very close, very far away from the orifice. So it's sufficiently far away to think that the velocity is negligible out here. It's an assumption basically.
Okay.
Or like,
okay.
Otherwise, the derivation is very complicated. You have to do differentiation and stuff.
Okay. Thank
right?
you.
Like for engineering, you use this assumption, and it gives like good results. If you want, I can like later I can find your derivation or something. Okay. So, any other questions? All right. Okay. So this is in like ideal conditions when the water in here, it flows out exactly as the same as the orifice thickness. The water level flows out in the orifice thickness exactly as you want it. But actually what happens is that when it flows out through the orifice, look, I'm zooming this, okay? So this is the orifice, okay? And this equation that we got, V equal to under 2GH, is in ideal conditions when the water just flows out like this. But actually, since our world is not ideal, this is ideal cases. I wish it could be ideal, but it's not. What happens is the water flows out like that. It actually misses, it goes out like this. So there's an air gap out here. It's called a contraction. The actual area of flow is different. So in here, if you calculate the Q Q is equal to area into velocity. So what you'll do is you'll multiply the velocity with the area of the orifice into A. But here, what to get the velocity, again, if you use 2gh, then to get the flow rate, you have to multiply it with the actual area, A dash into under root 2gh. So to account for that, they give up this thing. People, the scientists, made an empirical equation. So the actual area is, you make a correction into the area of the orifice into under 2gh. This correction is mostly, it depends on the type of the orifice. If it's a square orifice, it's different. If it's a rectangular orifice, it's different. But for as a conservative approach, you can, it's actually taken as, C is taken as 0.62. So the actual flow rate is always 0.62 into A into under root 2gh. Okay, it's like a correction for the contraction in the wall. Right, and this is called the orifice equation. Okay, so we'll try to solve a problem together on this. Let me find it. Wait, go. It's one of the handout problems, and okay. Okay, let me share it. Okay, try example 5.1. Oops, I should. Okay, do this example. It's quick, so I'll give you 5 minutes. Can you see the question? Yeah, you can see the question. Okay, let's start it. So just plugging the equation. So what did it say? Find Q. Q is equal to A into correction, A into under 2GH. So correction 0.62, and you need to find area 2 into 9.81 into H. What is the head difference? You need to find H. So you find A, you need to find H. So if you always anytime you're confused, always this helps. Take it to be what they see here, the ultimate truth. Always draw a diagram, and in physics, always draw a free body diagram. This one helps a lot to understand what's the problem. You may forget everything, but the free body diagram will help you understand everything. Okay. So what I'd say, the water surface elevation of the impoundment is 220 meter. And the elevation of the center of the orifice is 200. So what is the head difference? What is the head difference between this and this is 220 minus 200 equal to 20. The units are not given, so even I'm not putting the units out here. And now area. Area is, for the area, the diameter is given. Diameter of the this thing is given 6 inches, which is half feet. Yeah, 0.5 feet, right? Let's see. I don't know, 6 inches. Yeah, 0.5 feet. Okay. Okay. So the radius is by 0.25 feet, half of the diameter. So the area is pi into 0.25 square, 0.196 square. Okay. Okay, so everything is given in feet. So I think this is in feet. Okay. This book is English, so everything is feet. Okay. What book is this? Doesn't put the units. So Q is this 0.62 into 0.196 into 2 into 9 point, you can see it, right? Yeah. 9.81 into 20. So the final answer is 4.4. Now what's the unit? This is feet square. Okay. And this is feet 9. Oh wait, I can use 9.81. Sorry, it's in feet. See, I'm making this mistakes every time. That's why units are very important. 9 point acceleration of gravity is 9.81 in meter square per second. Meter per second square, sorry. Meter per second square. But now what you're doing out here is in feet. So you always use 32.2 feet per second square. So this is 32.2. So units are very important. If you're planning to give a FE exam or something later, this always make sure your units are correct. Because like suggest paper, this class is very easy, but later this engineering, this unit, you'll get these equations a lot. So be careful with the units, okay? So, and this is feet per second square, and this is feet, okay? Feet square, yeah. So feet square, second square, when it comes out of the square root, it becomes feet per second. So feet per second into feet cube square gives feet cube per second, which is cubic feet per second, CFS. Okay, so that's why units are very important when making your answer. See, I made a mistake right here. Think about it. Okay, now let's try. Now let's go to beer flow. Just pause it for something.